Hey everyone, welcome to our first lesson in Unit 11 on acids and bases, where we're going to learn about what constitutes an acid and a base and what makes a substance acidic or basic. Today we're going to learn about Arrhenius acids and bases, and you'll be able to describe properties of both Arrhenius acids and bases, and we'll take a look at a few different types. And then we'll use Table M to determine the pH of an unknown solution. So to start, Savante Arrhenius, who was around in the mid 19th to early 20th century, was the first to describe the conductivity of electrolyte solutions. Now we learned about this last unit, as ionic solutions do conduct electricity because they are considered electrolytes. And he hypothesized that solutions that conduct electricity have to contain some type of dissolved ion that's going to carry charge throughout the solution. He also described acids and bases in terms of their properties. So not only were they able to conduct electricity, since they are considered electrolytes, but he was able to describe them in terms of their varying properties. We're going to take a look at the Arrhenius definition of acids and bases. And there's a few different types of acids and bases as far as definitions. Today we're just going to focus on Arrhenius acids and bases. So as far as that definition, an acid is a substance that contains H plus ions that dissociate or ionize when they're dissolved in water. For example, if we take hydrogen chloride, or more commonly known as hydrochloric acid, and we add that to some water, what this HCl is going to do is donate a hydrogen to the water molecule here, and it's going to create this special ion, H3O+. And since HCl contributed that H plus into this solution here as a product, it is considered an acid. It's quite a simple definition. So it's a substance that contains H plus ions that ionize in water. So another example here, H2SO4 contains a sulfate ion and two hydrogen ions connected to it. These two hydrogens from this hydrogen sulfate, otherwise known as sulfuric acid, it's going to add those two hydrogens to these two water molecules, and we're going to create two more of these special H3O plus ions. So since H2SO4 is contributing H plus ions into this overall solution, it is considered an acid. And varying types of acids are going to contain a different number of H's that can be removed when they're combined in solution. So this special ion that we've been talking about is listed on Table E, your table of special polyatomic ions or selected polyatomic ions, and this one's called hydronium. And it looks just like a water molecule, but it has one additional hydrogen attached to it, which is an indicator that an acid contributed the H to this spot. So some properties of acids. And we'll connect some of this to Table J, as you can see there. So acids eat away or oxidize active metals. And these are going to be metals that are above hydrogen on Table J. So if there's an acid that's combined with one of these metals, the acid's going to oxidize any of the metals above H2 on that list. And in our next unit on electrochemistry, we will use a lot of Table J, because depending how we combine different substances, we have more aggressive or active reactions, or sometimes less aggressive or less reactive reactions. All depends on the substances that we combine together and how active they are. If we combine an acid with one of these three here, copper, silver, gold, it is not going to oxidize. So those three, if we were to combine that with an acid, are going to be unreactive. Acids have a pH less than 7. It's important to know. And acidic solutions conduct electricity. So we call them electrolytes. Now, if you've ever had any type of acid, common one that we get a lot, vinegar, lemon juice, if you get any of those diluted or even close to fuller strength, they are pretty sour. Now, to name acids, we are given a lot of common acids on table K. That's where I'll tell you to look first because most of them will be listed there. And this one in particular, ethanoic acid or acetic acid, which is vinegar, is written a couple different ways. So to name these, we can first check table K to see if it's listed there, and we can just take the name directly from there. If it's not there, we're going to have a little set of rules here. We're first got to figure out if it's binary, if it's hydrogen in a nonmetal, or if it's ternary, meaning hydrogen with a polyatomic ion. It's a lot easier if it's binary. If it's binary, all we do is add hydro followed by the nonmetal ion name. And we replace the last syllable of that nonmetal ion with ic acid. So as I was saying before, if we had hydrogen chloride, since this is an acid, we add hydro to the front, we replace the chloride with the end of it with ic acid, and this becomes hydrochloric acid. If it's ternary, just guess. Just kidding, don't really guess. If it's ternary, we want to first look at table E, where we have our list of polyatomic ions. But we're not going to use the hydro prefix. We first want to look at the ending of the polyatomic ion name. And if that polyatomic ion name ends in IDE or ATE, like carbonate or chlorate, then we're going to use the polyatomic ion name and then just add ic acid to the end of it. If the polyatomic ion name ends in ITE, like chlorite or sulfite, we're going to use the ion's name plus us, or us acid. We'll take a look at a couple examples because that makes it a whole lot easier. So IDE or ATE becomes ic acid, and ite becomes us acid. So HNO3 contains a nitrate polyatomic ion ending in ATE. So therefore, we're going to use the ic acid. So we get nitric acid. HNO2 contains a nitrite ion, ends in ITE. So therefore, we add the us acid to the end of it. So we get nitrous acid, nitric and nitrous. And if we trace this back, the only difference here is that one of these has 2 oxygens and one of them has 3 oxygens. HClO3 contains a chlorate ion ending in ATE. So it'll get the ic acid ending. So we get chloric acid. And HClO2 contains a chlorite ion. Anything ending in ITE gets the us acid ending. So chlorite becomes chlorous acid. We'd normally read this as hydrogen chlorite. We drop the hydro or the hydrogen, we just use the polyatomic and it becomes chlorous acid. Bases. What is a base? The best way to remember this is the saying that you see right there. Oh, it's a base. So bases are substances that contain hydroxide ions dissolved in aqueous solution. So now that we have OH, if we think about this, an acid adds an H and a base adds an OH, and together these will make water. For example, NaOH, sodium hydroxide. We have a hydroxide ion. This is on table E. It's a polyatomic ion. If we add that into water, what we see is that this completely dissociates And we end up with sodium ions and hydroxide ions. And that's our indicator that we have a base or an Arrhenius base. So bases have a pH greater than 7. Remember, acids are lower than 7. 7 would be neutral. Basic solutions do conduct electricity, just like acids. So these are electrolytes and will conduct electricity. Bases taste bitter, kind of the opposite of what acids would taste like, which are sour. And bases are formed when group 1 and group 2 metals react with water, which would then release hydrogen as hydrogen gas. Bases also hydrolyze fats, which means it turns the fat into a common substance called soap. And this is done through a reaction that we call saponification, which is an organic reaction, which we'll learn about later in the year. To name bases, this is a lot easier than naming acids. All you have to do, look it up on table below. We won't really see any other bases besides what you see there. If you do, it'll be a metal combined with hydroxide, and all we do to name that is the metal name combined with hydroxide. I'm going to do a quick little run through that just kind of shows you what we mean as far as acids and bases. I'm going to show you a couple different things here. So water by itself, and we have the reaction down here, what's actually happening. Water by itself will dissociate very little into a hydronium and a hydroxide acid and base. And we can add in here, if we look at this inside this container of water, we can show the solvent. So now we're looking at the solvent, which is all the individual water molecules. And inside all of this, all we have is 2 little molecules of hydronium and 2 molecules of hydroxide. And if we look at this on the graph, at equilibrium, our equilibrium concentration, moles per liter, we have our water and a pretty small concentration of hydronium and hydroxide. And these are going to change depending on what type we have here. Now we can put this little pH meter in here and we can test the pH. It'll tell us here, okay, this is 7. So this is considered neutral, not acidic or basic. And we'll go right down the line. We'll start with a weak acid. Now the weak acid, we have our acidic substance and water, and this dissolves or dissociates. The hydrogen comes off the acid and creates H3O+. Now in here, we can use a solvent or no solvent. I kind of like seeing the solvent down there. We have more hydronium in here than we saw with water. Okay, and if we look at a graph, the concentrations are much higher. Several factors of 10 there. Now this will change. If we look at the pH here, we said that pHs of acids were less than 7. So if this is an acid indicated by the H2O+, if we put the pH meter in here, this should be less than 7. And it's 4.5. Now we can use this without a meter, or with a meter, or with pH paper. And since the pH was 4.5, we should see a color in the medium orange range, which we get there. Now a strong acid, the difference there, you can see the reaction's close to being the same, but the weak acid has our double arrow here. This can reach equilibrium. The strong acid cannot. This reverse reaction won't happen because this strong acid fully dissociates and will not return back to its fully acidic form. So we now have many more hydronium ions here compared to the weak. And on the graph we see that again, 3 factors of 10 bigger or more hydronium with the strong acid. And if we put our meter in here, this should be, remember, it's got to be lower than 7, and our weak acid was 4.5, so would this be more or less than 4.5? It is less. So the lower number means this is more acidic. And if we use the paper down here by 2, it's going to be more towards the red side. And that's what we see there. Now these acids, whether strong or weak, since they have dissolved ions in here which have charges, these should be able to conduct electricity, just like our ionic substances. So if we put the leads in here, we see the light turn on. And if we use the strong acid, we see the light is even brighter. So weak acid will conduct. There are dissolved ions in there, but the more dissolved ions we have, the brighter our light's going to be. Now we'll take a look at a weak base. Again, I'm going to put the solvent in there. Weak base, we know bases have a pH greater than 7. Our base here dissolves in water. The hydrogen is removed from the water, and we end up with this OH hydroxide ion in the solution. Now, weak base, we have a few of these in here. If we look at the graph, we're going to have a concentration of hydroxide that is still greater than water by a couple factors. And we can see that we have a few different molecules in here. And the pH here we know should be greater than 7. That's 9.5. And we can do that again with the pH paper. 9.5 is going to be somewhere in the green. And that's what we get there. For the strong base, we see, again, a single arrow here compared to the double arrow. So this fully dissociates in the solution. That's a key of strong bases. They fully dissociate, whereas weak bases won't fully dissociate. We have a higher concentration of hydroxide. And again, we see that with our factor of 10 here, with our concentration of hydroxide. And if we were to measure the pH of this, we'll start with the meter. This should be greater than 7, and it is. And it's higher than our last reading with the weak base. If we put our paper in here, we should get something a little bit more towards the darker green, towards blue end, which we get there as well. Now, if we check the conductivity here, the weak base, just like a weak acid, this does conduct, but if we do this with a stronger acid, more dissolved ions, we have a much brighter light because we have more ions to carry the current from this pole to this pole. And the last thing we'll talk about is how we can determine if a solution is acidic or basic. We just saw we could use a pH probe, which is pretty nice because it gives us a nice, quick, easy digital readout of what the pH is. But we can also use acid-base indicators, which is much more practical and cheaper to use, although a little less accurate. Now, the indicators are chemicals that have a certain color that is shown depending on the pH of the solution in which it's inserted. So they can be used to determine if a solution is acidic or basic, or narrow the range of a pH, but it won't give a specific pH. We need a meter for that, or some kind of complex math. So pH paper is paper soaked with a mixture of different indicators that give a specific color at a specific pH. And that's what we just saw in that simulator there. Litmus paper, which you guys would have used in biology, is paper soaked with litmus solution that has been allowed to dry, which will then indicate whether it is acidic or basic. Now, table M gives us several different indicators, and it gives a range for the color change that occurs, and then tells you what that color change will be. So if we use methyl orange, I'm going to use this as an example. If we use methyl orange as an indicator for a solution to see if it's acidic or basic, we're only going to see 2 to 3 colors. The indicator is either going to show red or yellow, or an intermediate color as we see a transition from red to yellow. So methyl orange is red. I kind of read this left to right. 3.2 to 4.4 red to yellow. So methyl orange will show red from a pH of 3.2 or lower. So anything at 3.2 or lower, we're going to see a red color. So if this is a pH of 1, it would still be red. If it's a pH of 3, it would still be red. We only see a change here across the range. And this is going to be yellow from a pH of 4.4 or higher. If we get a pH somewhere in the middle there, like 3.6, 3.7, 3.8, we're going to have an intermediate color, something that'll transition from red to yellow, which in this case would be orange. I'll run through a quick little sample problem of how we can use this to indicate the pH of a solution. So we have a solution that yields the following results when tested with various indicators. Methyl orange, it gave a yellow result. Phenolphthalein was colorless. Bromcresol green gave us a blue result. And thymol blue gave us a yellow result. So each of these results comes as a result of a pH falling somewhere in those ranges. So could the pH be 2.8, 6.5, 8.5, or 4.8? Well, let's try and rule them out. Methyl orange. Methyl orange is yellow at pHs above 4.4. It's red at pHs below 3.2 and changes from red to yellow between 3.2 and 4.4. Since the pH must be above 4.4 because of the yellow color, we can eliminate choice A. It's got to be above 4.4. Phenolphthalein is colorless at pHs below 8.2. So we see that here, colorless below 8.2. Since we got a colorless result, 8.5 is not going to work because that's higher, and therefore we would have gotten a pink result. Bromcresol green is blue at pHs above 5.4, and that's what we got, was a blue result. Therefore, we can eliminate D because that is less than 5.4. So you can start to see how we can use different indicators with different ranges to start to narrow down our pH. Because if we just use methyl orange, all that we would know is that, well, the pH is above 4.4. It could be 12, it could be 9, it could be 4.5. We don't know. It's all the same color. So this helps us to eliminate some of the other ones. Thymol blue is yellow at pHs less than 8. 6.5 is less than 8, so therefore the solution would have to have a pH of 6.5. Make sure you guys write down any questions that you have and ask them when you get the chance. Have a great day.